let's go ahead and get started. Thanks everyone for coming. It's great to see you all in the participants list. So I'd like to welcome you to the optimization and optimal control session this morning. And I want to note that this session is in the new rapid interactive format that we're trying out this year for the 2020 ACC. So the morning talks are all in the rapid interactive format and the afternoon talks are in the traditional format this year. I want to point out in the chat that we have a couple of links there in the chat. One is for the People's Choice Award. So please vote on your favorite talk in this session. There'll be 22 of them. And also consider nominating a paper for the Hugo Shuck Award. So those links are both in the chat. And we'll be taking questions for Fumin in the Q&A feature. So not in the chat, but in the Q&A, and he'll be able to answer those through the typing during his talk as it plays. And then also we'll have about 5 minutes afterward for questions that he can answer live. And then then after Fumin's keynote address, we will have these 3-minute rapid talks. And then that will be followed at 11 o'clock by an interactive session where you can go visit speakers where you're particularly interested in their talk and ask them questions. So, but right now I'd like to get started with our keynote presentation and introduce Fumin Zhang from Georgia Tech. So he's presenting a paper by Nixing Yao and Fumin Zhang, Optimal Real-Time Scheduling of Human Attention for Human and Multi-Robot Collaboration. And so we'll go ahead and listen to his video, but Fumin is here and can answer questions in the Q&A. Thank you, Fumin.
Hello, we'll discuss the paper, Optimal Real-Time Scheduling of Human Attention for Human and Multi-Robot Collaboration System today. This work is done by my PhD student, Nixing Yao, and I. We are studying the problem of a human operator collaborating with a swarm of robots. The question is, which robot should the human operator to work with at any given time? On the other hand, the robot can work in either autonomous mode or interactive mode. For the robot, we want to decide which mode should the robot be operating on at any given time. So human-robot interaction is a new trend in control. Professor WeA01 and I have co-edited a book that recently has been published. We want to solve this human-swarm-robot interaction problem in the context of real-time scheduling. Here, the human operator's attention is viewed as a resource that multiple robots trying to access. When more than one robot trying to access this human's attention, demand the human attention at the same time, we need to resolve a contention. In real-time scheduling, we resolve contention by assigning priorities to different tasks. In this case, each robot's requests are viewed as a task. For example, given these two tasks, the red task and the blue task on the screen, which task should we assign higher priority? In real-time scheduling theory, the answer is we should assign the red task higher priority because it has shorter periods. Modeled from this perspective, the requests from robots are modeled as tasks. And here we have a green and yellow and and red robots, all requesting access to human, to interact with human. And then C here models the time it needs to interact with human. And T here, capital T here, represents the task time. So each robot needs to interact with a human every now and then. So T models how often each robot needs to interact with human. And then there are other important parameters here. This alpha is the arrival time of each request, and gamma models the finishing time of each request after human process it. And delta are the time delay between the request and when the resource is granted. So every task here is non-preemptive. In other words, if a robot started interacting with a human even if higher priority robots try to access the human, the access will be denied. It will be granted only after one robot finishes interacting with human. So in this setup, we want to assign an optimal priorities to maximize the overall robot performance. Therefore, we need to introduce a model for robot performance. So here is our robot performance model. We assume that robot performance will decrease when work in autonomous mode. This is modeled by this red curve. And then we assume that robot performance will increase when collaborating with human operator. And then this is modeled by this green curve going upwards. And here are the equations for the two modes, for the autonomous mode and a interactive mode. And then this decision variable u here assumes only two values, either 0 or 1. So when u equals 0, that means the robot is working in autonomous mode. When u equals to 1, that means the robot is interacting with the human. And then for each robot, there is a minimum performance here, modeled by PI mean, and a maximum performance modeled by PI max. This mathematical model guarantees that the performance will not be bigger than P max or smaller than P mean for each robot. And then we want to model the timing that the human have to obey to interact with this robot under any type of attention allocation scheduling algorithm. Our previous work has suggested us to use timing model to model these the timings of a set of scheduled tasks. The timing model is based on 4 state variables. So the first state variable is called dynamic deadline. This is given the current time t here, what is the deadline for each of these tasks? And then the second state variable is called remaining time. Given the current time, what are the time that is still needed to finish each task? And the third state variable is called delay. This is the time between when a robot requests interaction until it finish and it finish the interaction. And then the fourth state variable is this IDT. This indicates which robot is currently interacting with a human. If no robot is interacting with a human, IDT will be 0. Given these 4 state variables, the next important concept in the timing model is called significant moments. The significant moments are the moments where the state variables has sudden changes. Okay, as illustrated by this figure, all the Ks, K0, K1, K2 until K13, these are all the significant moments within this time period between 0 and 24 of a set of scheduled tasks. We can see that these significant moments are either corresponding to the time when a robot made a request, which corresponding to the up pointing arrow, and then when the robot finished interacting, corresponding to time where we have this downward pointing arrow. And the idea of the timing model is we only need to model the changes of these state variables at these significant moments, because at these significant moments, they have jumped, which is all the set of equations on the left-hand side. And then in between the significant moments, the models for the state variables are relatively simple, as you can see on the right-hand side blocks. The details of these timing models can be found in our previous papers on real-time scheduling. With the help of timing model, we can now formulate an optimal scheduling problem as a model predictive control problem. So we want to have the timing model and the robot performance model to predict the performance of robots in a finite time window. And then after we decide the optimal schedule, we're going to apply the first instance of the schedule, and then we move the horizon forward and redo this process. So here our MPC cost function is formulated to maximize the overall performance of the robot. Okay, it's corresponding to minimize the difference between the performance of each robot and its maximum possible performance. And then the constraints are the performance model, which we have already discussed. And then the decision variables are assuming a value of 0 and 1, right? But these values are only hold constant during intervals that the length of these intervals can be computed by the timing model. Without the timing model, we cannot formulate this problem. Okay, now let's talk about how we can solve this problem. Because the decision variables are integers now, so this is actually a mixed integer programming problem. It's kind of difficult to solve, but in this case, because of the timing model, we can actually construct a decision tree for optimal scheduling to solve this problem quickly. So each node of this decision tree corresponding to a moment where a contention happens. For example, the node 1 corresponding to key 1C, where there's 3 tasks having contention. So we can decide which task can be allocated the human's attention, and then this corresponding to 3 branches. And then get to node 2, 3, 4. The node 2, 3, 4 corresponding to K2C when contentions between 2 tasks happens. So and then we have 2 branches. So we can just keep doing this with the help of the timing model to predict when the contention can happen, and each contention corresponding to 1 node in this tree. And then we can use the MPC cost function to calculate the branch cost that characterize the robot performance for each branch. In other words, in between each possible contention. This tree looks pretty complicated. However, we actually do not need to construct the entire tree in order to find the optimal schedule. In this case, the optimal schedule corresponding to the shortest path marked by these red arrows along this tree. So our job is to conceptually understand this tree, but then use a smart algorithm to search for the optimal path without constructing the entire tree. So I want to say a few words about calculating the branch cost. Calculating branch cost is straightforward because along each branch, we actually already get the decision variable. We know the value of decision variable. And then use our timing model, we can actually construct the branch cost as this WLJ. Okay, and the details you can see our paper on how to do that exactly. Conceptually, once we understand this is a decision tree, then we can use smart tree search algorithms like A* to find the shortest path without constructing the entire tree. If you worked in the robotic field, then you know A* pretty straightforward. It's a pretty straightforward approach. It keeps the cost of arrival and a heuristic on cost to go. And then it searches tree by sorting each nodes according to this summation of cost arrival and the heuristic cost to go. Okay, and to do this, A* searches the most likely nodes first for the shortest path. So another aspect of A* is an algorithm where it constructs the tree while searching it. So oftentimes it's able to find the shortest path without constructing the entire tree. And this greatly reduces the computational time. And we can actually prove that under certain technical conditions, the optimal scheduling solution found by A* search is actually optimal. And here, I'm showing a simulation results of 3 robots competing for human attention and the optimal allocation computed by our algorithm. On the left-hand side are the human attention allocation for each robot, and on the right-hand side is the robot performance. You can see robot 1 always has the highest priority among the 3 robots. Why is that so? If you look into the parameters of the system, you can see that robot 1 actually has the smallest minimum performance. Okay, and also robot 1 has the most frequent request for interacting with the human. So actually it's not surprising from a real-time scheduling perspective that Robot 1 should be given a higher priority because we want to make sure the overall performance is maximized by interacting with Robot 1 more often. In our lab, we actually have robotic blimps that are able to interact with human safely. So in this experiment, an undergraduate student, Yu Qi, she is trying to interacting with two flying blimps by making the blimps follow her wand. So when she is facing one of the blimps, the blimp will fly better, will follow her wand better. When she is turning away from that blimp, we add noise in the motion of the blimp so that the blimp performs worse than when she's facing it. In this case, our algorithm is computing suggestions for her regarding which blimp she should interact at a given time. So due to the COVID, we don't have enough data to say anything concrete, but we hope that we can repeat this experiments more on more subjects so that we can present results next time when we talk about this topic. That's the end of my presentation. Thank you.
Okay, that's not that bad.
Great. So we had a couple of questions going on. I think there's one open question right now. So maybe I'll just go ahead and read that. Have you guys looked at cases where all robots actually get less efficient when working with a human, maybe simulating human that needs to pause the robot's operation to make repairs or something?
Oh yeah, that's actually a great suggestion. So far, we assume when the robot working with human, the performance will increase, right? What if that assumption is wrong, right? I mean, that will make this problem much more complicated, definitely. And also there was another great question on considering uncertainties, right, in the robot's behavior and human behavior using MDPs. So the key of this talk is event-driven MPC actually, but we call the events a significant moment because it's associated with our timing model. So that's definitely, you guys are fantastic because you're already thinking about future directions to go, right? You can help me solve this problem. So thank you so much for your attention.
Fumin, I have a question for you.
Right.
So is this formulation that you have, do you think that it can apply to other problems that are not only these human-robot interactions now that you formulated it, or is there something really unique about the human-robot problem that leads to a unique formulation?
Yes, actually, in general, timing model applies to any time when you have a contention. For example, traffic intersection, that's one of the problems we look into, and also scheduling on real-time bus with different control loops. Those are papers we published before. One unique thing about human-robot interaction is the human capacity is very unique. Here in this paper, we only consider linear capacity, like the more robots human can interact with, the better, right? That's not true, right? You don't want more tasks than you can bear, right? So there was actually a previous paper we published consider like a psychological model on the number of tasks assigned associated with the human performance. So in this paper, we didn't consider human performance. If you think about it, human performance is actually very important to consider. Yes. So I think
that
in the journal
version
might be the
stochastic part. The
exactly, and
so
even deterministic. There's this curve called Eve's distance theory that tell you that you cannot just keep giving people tasks and expect they perform well, right? So which is obvious, right? So
I don't think professors know
that. Of course, our threshold probably are higher, right? But
maybe not.
That's perhaps why we're sitting here. But anyway, so yeah, so that's I guess that's that's an easy not I say easy. That's probably the immediate next step we'll do. Right. Yeah. Oh, okay. So
okay, let's
okay, I'll
let's take one last question from Ethan. Do you want to just read that, Fumin? And
yeah, can you
and then we'll wrap up.
Yeah, can you use the same model in the case where one robot's interaction period changes to become more or less of a priority? Here, our priority does not depend on, it's agnostic to the period, to the time change. So if you time change, because we compute everything as MPC online, if you time changes, we can still handle it. I guess you're thinking about designing the control of the robot, right? So the co-design, the control of the robot and scheduling, so that the overall performance get better. That's a great problem. We look into similar co-design problem in other context, but not in this context before. So feel free to check our papers on traffic scheduling. That's a case where you can co-design those. Yeah.
Okay, thank you so much, Fumin.
Thank you, everyone. Yeah, this works really well.
Thanks for all the great questions. So that's our keynote address. And now we're going to move to the rapid part of the presentation, or part of the session. So please stay in this Zoom room for the rapid presentations. They're going to go until 11 o'clock. And we're going to have one video that plays, and we're going to listen to 21 3-minute presentations. And please do use the links in the chat to vote for your favorite presentation. You know, wait till the end. And also consider for the Hugo Shuck Award. So those are both in the chat. But please stay in this Zoom room. Now at 11 o'clock, then you can go to the interactive part of the session, go back to the main conference program, and you can visit any of these presenters in their own Zoom rooms, have their own Zoom links in the main program. But don't go there now. Stay here and enjoy these 21 3-minute presentations.
Hi, I'm Alex von Maul, and I'll be presenting our paper on optimal evasion against dual pure pursuit. The scenario involves 3 agents with simple motion, meaning the agents control their instantaneous heading. They have a fixed speed, and the pursuers' speeds are equal and greater than the evaders. We fixed the pursuer strategy to pure pursuit, which is always aim at the evader, and we're interested in determining the evader's control to maximize the time at which one or both pursuers comes within the capture radius. Termination occurs when the distance between the evader and a pursuer is 1. There are 2 cases. One or other pursuer affects capture alone, or both pursuers affect capture simultaneously. In solo capture, the evader and capturing pursuer's trajectories are straight. E runs directly away, and capturing P runs directly towards. The non-capturing pursuer is redundant. In dual capture, generally all 3 trajectories are curved, and there is no analytic solution to the optimal control problem. It is obtained numerically by solving a 2-point boundary value problem. For solving the 2-point boundary value problem for dual capture, the free variables are the terminal pursuer half angle and the terminal evader heading. Fortunately, we can bound the range of admissible or potentially optimal headings as shown. We can partition the state space based on how the optimal engagement will terminate. The separating surface is computed by considering the limiting case of solo capture, wherein the redundant pursuer's terminal distance approaches 1. Lastly, here are some representative trajectories in each of the regions. The first is solo capture by P1, wherein P2 terminates with distance greater than 1, as shown here. The second is the limiting case wherein P2's distance is 1, but the solution would be identical if P2 were removed. The third is a general case of dual capture wherein all 3 paths are curved. Finally, the fourth is a special case of dual capture wherein E's path is straight. This only happens when E starts on the bisector of the pursuers. Thank you for your attention.
Hi, my name is Alex Schenker from Los Alamos National Laboratory, and today I'm going to tell you about using extreme seeking to create optimal feedback controls for unknown systems. So the method I'll be using is extreme seeking for stabilization and optimization of unknown, time-varying, and open-loop unstable systems, which was recently developed. And here are references that give you some more information about this method. So the main problem is to find optimal controllers for unknown systems. Now, if you...
Hi, I'm Alex von Mall, and I'll be presenting.
Hi, my name is Alex Schenker from Los Alamos National Laboratory, and today I'm going to tell you about using extreme seeking to create optimal feedback controls for unknown systems. So the method I'll be using is extreme seeking for stabilization and optimization of unknown, time-varying, and open-loop unstable systems, which was recently developed. And here are references that give you some more information about this method. So the main problem is to find optimal controllers for unknown systems. Now, if you actually have a linear system and you know the dynamics exactly, and you know the trajectory you want to follow exactly, and you analytically know the cost function, there are methods that give you the exact global optimal solution. And in the approach we're taking here is some of the benefits of it are you could have a linear or a nonlinear system. You could have unknown dynamics, an unknown trajectory that you want to follow, and an analytically unknown cost function. All you actually have about the cost function is a noisy measurement, but you don't know what it actually is. And you can create arbitrarily accurate, globally optimal solutions when the cost function is convex, which is the case for linear systems, which I'll show you in the next slide. And some of the limitations of the method are that it's iterative, it's an approximation method, and you need the system to be repeatable over time to learn these optimal controllers. But the basic idea is you represent the controllers in terms of a basis functions over the Hilbert space, which is in this case the L2 square integral functions over the interval 0 to t. And the coefficients of those basis functions, you tune them according to this extreme seeking method, which just needs access to noisy measurement of the cost function, and it ends up minimizing it. So in this example, I'm showing you just a two-dimensional system, two inputs and two outputs, and the difference between the X and Y system is just their initial conditions are different, but dynamics are exactly the same. And we want to learn an optimal feedback control for the system. And what we need is just two linearly independent initial conditions. And what we do is we know that the optimal feedback controller needs to take this form, which would from the analytic solution. So what we do is we parameterize this feedback matrix by basis functions in this Hilbert space on the L202, 0t of the time interval. And then we use extreme seeking to adaptively tune these coefficients to simultaneously minimize the cost function associated with both these initial conditions. And here you see it happening, and this method finds out this exact actual feedback control matrix that gives you the optimal feedback controller. And this is just comparing the trajectories that the extreme seeking found and the optimal feedback trajectories you'd have if you analytically knew the system. And because we have this feedback controller now for a new system that we haven't seen before with new initial conditions, we again generate the optimal trajectories with optimal feedback control.
Hello, everyone. Thanks for coming. Our paper analyzed a specific homotopy algorithm named damping with the hope of finding a globally optimal decentralized control.
Hi, my name is Alex Schenker from Los Alamos National Laboratory, and today I'm...
Hello, everyone. Thanks for coming. Our paper analyzed a specific homotopy algorithm named damping with the hope of finding a globally optimal decentralized controller. Our homotopy method can be combined with any local search or path tracking methods. We showed that damping effectively reduces the number of locally optimal solutions. Homotopy algorithm is widely applicable but poorly understood. The ideas of varying the system matrices have appeared in other control problems. The novelty of this work lies in the justification of this specific type of homotopy in optimal decentralized control problems. Damping is defined by varying the A matrix of an LTI system by minus alpha I. Here, alpha is a parameter that controls the amount of damping, and the parameterized cost J alpha is quadratic. We showed that gradually varying alpha improves the landscape of the cost function J alpha. As this slide shows, even though the problem is non-convex, by optimizing over J alpha with a positive alpha, there is a hope of arriving at a better locally optimal controller. How good are the optimal controllers with positive alpha? Under assumptions on the sparsity pattern of the controller and on penalty matrices, we should prove that when alpha is large, Even though the problem is non-convex, all locally optimal controllers are globally optimal. This figure plots the costs of locally optimal controllers against the damping parameter alpha. For large alpha, there's only one curve. Can this good controller with large alpha be related to the optimal controllers when alpha is equal to 0? We show the continuity properties of the homotopy path with the notion of epicontinuity. As a result, the costs of locally optimal controllers will always look like this set of decreasing continuous curves in the figure. This implies that path tracking is possible. These two observations are combined to show that this following homotopy algorithm is able to optimally solve the decentralized control problem under certain conditions. In the extended version of the paper, we consider varying the costs Q and R function matrices as well, and also show that there are difficulties of extending our results to alternative homotopy regimes. To summarize, our paper showed that for ODC problems, a homotopy method named damping effectively reduces the complexity of the problem. Thank you.
Hello everyone, my name is Christoph Horn and I'm here to present the paper titled Energy Optimal Tools for Hello everyone, my name is Christoph Horn and I'm here to present the paper titled Energy Optimal Tools for Quadrotors to Scan Moth-Infested Trees in Densely Packed Forests. We start off with a motivation where pine processioning moth infestation has gone rampant in Lebanese pine forests. In order to detect moths, we use a quadrotor which flies to the bulk and scans them. However, it needs to maintain an aerodynamic distance described as the red zone, while at the same time maintaining a close distance, which is portrayed in the blue zone. In order for the quadrotor to travel between one tree and another, an optimal control theory is used with a generalized energy consumption cost function while respecting path and dynamic constraints. However, in order to solve this optimal control problem, we use a hybrid method with a various discretization and optimization method to check for convergence, minimize constraint violations, and minimize the energy consumption in total. After determining the energy consumption between each pair of trees, and in order to determine the global optimal tour, an asymmetric traveling salesman problem is formulated, and it is solved using integer linear programming and subtour elimination constraints. After determining the global optimized tour, a prioritized subtour could be made using the probability of infection. As the quadrotor is touring throughout the forest, the POI is actually updated, and then a cutoff margin is done in order to prioritize certain trees, and using the fixed start, fixed end traveling salesman problem solution using a genetic algorithm, a new tour is done. In order to verify our theory, we use two platforms, which are the DJI Phantom 2 and the CrazyFly 2.0, and they are used due to the variations in sizes and dynamics. As you can see, the CrazyFly consumes 1 kilojoules of energy while doing a tour with single base and 10 trees. On the other hand, the DJI requires 40 kilojoules and 27 seconds in order to traverse the same map. As you can see, a prioritized subtour is established, but however, as the quadrotor traverses from one tree to another, the tree 10 is dropped due to its low probability of infection, which goes below the cutoff margin. To summarize, we use the hybrid discretization method in order to find the global optimal path planning between two trees for the least violation of constraints and the least energy consumption. Moreover, in order to determine the whole tour, we use ILP and SCC for the global route planning. Moreover, in order to prioritize, we use POI for tree search, while in addition to an online update using genetic algorithm to solve FSFETSP. Thank you all for your time.
Hi everybody, it's my pleasure to present my joint work with Dr. Musavi to you. Hi everybody, it's my pleasure to present my joint work with Dr. Musavi to you. Here is the outline of my presentation. It includes two parts, introduction and numerical examples. To ensure a desirable level of closed-loop performance guarantee, we utilize the well-known H-infinity norm. H-infinity control is useful in disturbance attenuation. By resilience, we mean if the controller is hit by a perturbation, then the stability is still preserved. The source of perturbation could be round-off or modeling errors. To achieve lower levels of communication in large-scale systems, we are interested in Sparta promoting optimal controllers. In other words, we want to make the most of controller entries equal to 0. This result from 2004 is the building block of our proposed method. Firstly, we get a resilient dense F sub O with an H-infinity performance guarantee gamma for all of the controllers within the ellipsoidal region centered at F sub O. Then we cast parametric resilience ellipsoid as an LMI via short complement and then apply sparsification methods to get a sparse F. We use two sparsification methods, related L1 regularization and Grady algorithm. The following schematic figure visualizes the sparsification via exploration in parametric resilience ellipsoid centered at F sub O. Here we design F sub S by related L1 and F sub G by Grady algorithm for two classes of LTI systems. In case of randomly generated system, for F sub S, we have 35% sparsification at the expense of 7% performance loss, and for F sub G, we get 22% sparsification at the cost of 5% performance loss. For the class of especially decaying systems, we observe the Grady design outperforms the related L1. This slide depicts the corresponding sparsity patterns of F sub G and F sub S for two classes of LTI systems. As design parameter theta increases, we get sparser controller designs with higher performance loss. We observe for the class of randomly generated systems, the related L1 outperforms the Grady design in terms of performance sparsity trade-off. Running the experiment with 5,000 random perturbations, we observe the larger theta we have, the sparse controller is less resilient. Thank you so much for listening to my presentation.
Hello, I'm William Nagel, a PhD candidate in the Design, Automation, Robotics, and Control Lab at the University of Utah Robotics Center. This is work that I did with my advisor, Professor Cam Liang, investigating the cascading structure of LQT control for dual-stage nano-positioning systems. Dual-stage systems consist of two actuators, a long-range actuator, or LRA, and a short-range actuator, or SRA, connected in series so that the total system output benefits from the stroke of the LRA and the speed and the precision of the SRA. A common biological example for this is the human arm, with its elbow and wrist motion, though the most common application for this concept is the hard disk drive, where a voice coil motor moves a small piezo element attached to the read-write head. These systems can be modeled through spring mass damper combinations, although more complicated models can be used for more complex dynamic effects. Though beneficial, some challenges do arise through this actuator arrangement, through the now overactuated system dynamics, nonlinearities, and for general tracking applications where a priori knowledge of the reference isn't available. My work proposes to account for these challenges through linear quadratic tracking control. I'm interested in adjusting the structure so the actuators have separate references, where residual tracking error of the LRA is passed directly to the SRA. Models of a prototype dual-stage nanopositioner are used, where control is executed on a single lateral axis. Additional linear state observers are included to estimate states where required by the controllers. First, looking at the standard LQT structure for a DISO system. With performance index J, the optimal control law is defined by U star, along with matrix algebraic Riccati equation for P bar and a vector differential equation for G bar that needs to be solved backwards in time. A suboptimal real-time implementation can be achieved through negating that state matrix so the eigenvalues are negative, although tracking tends to lag behind the reference. I propose to separate the LQT structure between the two actuators so that there's more flexibility in their references. The performance indexes and the resulting control law solutions are the same structure as the standard LQT, but by selecting the LRA reference to be the entire trajectory and the SRA reference to be that residual tracking error, the SRA will explicitly attempt to compensate for that lagging effect that the LRA exhibits. This concept is demonstrated through simulations conducted on dynamic models of a dual-stage nanopositioner. Linear dynamics are modeled through swept sign measured frequency responses for both actuators of a single axis, and hysteretic actuators are modeled by cascading a Prandtl-Ishlinsky model with those linear dynamics. Both LQT controllers are calculated for low-order linear models of the system with similar performance index weights. Simulated results for triangle references on 3 plant models are conducted, and overall the cascading structure improves the tracking performance. The plant that matches the LQT model exhibits a drastic reduction in the RMS error with a slight increase in the maximum error. High order dynamics and hysteresis increase the error percentages for both controllers, but on average the cascading structure improves both RMS and maximum errors by about 50% from increased SRA efforts. I'd like to thank the National Science Foundation for funding this research, as well as you for listening to this talk.
Welcome to my presentation on iterative method for optimal control of nonlinear quadratic problems. The basic idea that motivated this paper comes from linear quadratic regulator problem, whose optimal control we know is a feedback form derived by first solving Ricardi equations. One application of LQR is for tracking. So in this paper, we focus on nonlinear quadratic tracking problem, which is defined similarly as that of LQR, but subject to a nonlinear control affine system with either linear or nonlinear outputs, where we don't denote our tracking target as Z. To solve directly for this problem would be intractable most of the times, and it would be interesting for us if we could adjust what we know from linear problems to cater for its nonlinear counterpart. So in this paper, we devised an iterative method where locally in each iteration, the techniques of linear problems could be borrowed and employed. The optimal control can be derived by applying HJV equations where we define value functions as of projective form of the states. And we will arrive at a set of ordinary differential equations. However, to solve these ordinary equations that are subject to some boundary conditions would be intractable in a way that it would involve 2 bounded value problems. If we could apply iterative method, however, we will arrive at a series of updating equations which are more straightforward to solve, since if we are looking closely at each iteration, we are solving for nothing more than a linear problem subjecting to a linear time varying dynamics. The convergence analysis is performed by first constructing a contraction map and then utilizing fixed point theorem as summarized as theorem 1 in the paper. To validate effectiveness of this method, we first apply this method to a nonlinear model of a chemical reactor with linear outputs to minimize the deviations of the states as well as minimizing the control energy. And we can see the result is very nice in terms of it's converging after 5 iterations. Also, we can apply this iterative method for a nonlinear model of a neuron with nonlinear output. And we can see from the result that it's nice and satisfying in terms of tracking the given target signal. So in conclusion, this paper devised an iterative method for finding optimal control of nonlinear control affine system while accommodating for linear outputs and some nonlinear functions. So in the future, we hope to extend this method to accommodate more general case of nonlinear systems, such as non-affine control system. Thank you for joining me.
Hi, thank you for your interest in my paper on how to use bi-level optimization for UAV trajectory optimization. Generating optimal trajectories in complex environment is hard due to the collision-free constraint, but necessary for many real-world applications. A widely used method is to construct a chain of safe corridors and constrain each piece of the trajectory to be inside its corresponding corridor. Besides trajectories in each corridor, the time allocated to each corridor has to be optimized too. Our method efficiently optimizes both trajectory and time allocation. Prior work either chooses a fixed time allocation by heuristics or optimizes time allocation using gradient approximated by Faraday difference. The first option gets a suboptimal solution, and the second is inefficient. Our contribution is we derive the analytical gradient for time allocation while previous works use Faraday difference. We construct a bi-level optimization framework to optimize time and trajectory. Our solver is anytime feasible, efficient, and gets better solution. This figure shows the idea of bi-level optimization. In upper level, we want to optimize Y, but the cost function has to be computed by solving another optimization problem in a lower level, which depends on Y in a non-trivial way. We performed numerical experiments on 100 randomly generated forest-like environments. The left side shows the obstacles, the initial and refined trajectories. The right side shows the safe corridor and trajectories for another example. The objective function, which is the integral of square jerk, reduces from 45 to 0.15, a 300 times improvement. We mainly compare three types of algorithms: our method of analytical gradient and baseline finite difference gradient, plus bi-level optimization framework. Another type of solver is joint plus NLP is to optimize trajectory and time allocation simultaneously using NLP. The third type is to use direct collocation method to formulate an NLP. Here, we show the results. Our method is about 3 times faster than finite difference baseline and has smaller suboptimality, which measures the quality of the solution. We believe it gets better solution since it has more accurate gradient computation. Joint plus NLP barely succeeds or improves the cost function. We believe it's caused by the strong nonlinearity of the problem. DC plus NLP is very slow, and its success rate is not great either. Here, suboptimality is not directly compared because it's computing a similar but different cost function. For real-time applications, we may set a cut-off time at 25 milliseconds. Our method achieves a much better suboptimality than the baseline. Thank you for your interest. Please see my paper for the details.
Hi, my name is Orlando. I'm a PhD student at RPI in New York, although I will switch to UPenn by the end of this summer to work with Professor George Pappas. So the research for this project was actually conducted. Hi, my name is Orlando. I'm a PhD student at RPI in New York, although I will switch to UPenn by the end of this summer to work with Professor George Pappas. So the research for this project was actually conducted mostly at an internship last year at Merle, supervised by Dr. Benesman. So imagine you have some cost function you're trying to minimize, for instance, via the gradient descent algorithm, which it is well known, it has a linear convergence rate of this form with the previous assumptions. And in continuous time, it can be interpreted as the so-called gradient flow dynamical system, which has kind of a matching rate of convergence, in this case exponential in the terminology of continuous time systems. And these two methods can be connected quite simply via the so-called forward Euler discretization. And as it turns out, many optimization algorithms can be connected with continuous time dynamical systems via discretization. So we're going to focus on continuous time because the hope is by discretizing, we can gain some insight into the corresponding, the kind of matching optimization algorithm. So as I mentioned, the gradient flow has kind of this exponential rate of convergence, which in practice means it will converge quite fast. But if we zoom in on any window of time, as we can see here, we'll see that in practice, we are kind of approaching the desired minimum quite fast, usually, but we never quite reach it in a finite amount of time. Of course, that's what asymptotic convergence means. So from a theoretical perspective, it is interesting the question of, can we design some sort of optimization algorithm that does converge in finite time and such that we can predefine the convergence time? So it turns out the answer is yes. What we actually need is this Lyapunov lemma that says if a candidate Lyapunov function decays according to this law, then it will actually converge to zero in a finite amount of time. So we can essentially now take this candidate of a Lyapunov function and then design some x dot that satisfies the previous inequality and therefore convergence in finite time. And this is just, for instance, a particular flow we designed to satisfy the previous, and therefore it converges in finite time. For instance, here we see on the Rosenberg function, has a minimum represented on the upper right corner in red. As you can see, for all the initial values we consider, we actually all converge exactly at the same time. Big T equals 1 second, which was predefined by us, by the user. Next, we actually extended our results for time varying optimization. So in the case where the cost function is non-stationary and the flow kind of looks like this by simple reviews of the previous argument. And here's a quick example where the solution is time varying. And as we can see, no matter where we start, so for instance, at position 50 or minus 10, we can choose to converge exactly time, for instance, 2 or 6 or 10, exactly as we wish. So I hope you found this interesting, and thank you.
Good morning. I'm Zhi He from Shanghai Jiao Tong University, China, working with Professor Jianping He, Cailan Chen, and Xingping Guan. Today, I will present. Good morning. I'm Zhi He from Shanghai Jiao Tong University, China, working with Professor Jianping He, Cailan Chen, and Xingping Guan. Today, I will present a novel algorithm to address a class of constrained distributed non-convex optimization problem. Distributed optimization makes agents collaboratively optimize a global objective, which is the average of a set of local objectives. It has various advantages over centralized architecture, including efficiency, robustness, and so on. Also, it has many applications ranging from distributed learning, localization, coordination, control of sensor networks, smart grids, and multi-robot formations. Since 2019, when DGD was first proposed by NETIC, many efficient distributed algorithms have emerged. They can be roughly divided into two classes, primal-based and dual-based. Here are some representative algorithms and descriptions of their general features. However, there are two notable unresolved issues. First, for most existing algorithms, the number of evaluations of gradients or values of local objectives grow with respect to iterations. This can result in large burdens in certain cases. Second, for non-convex problems, it is hard to converge to global optimal points. Motivated by these issues, we developed CPCA. Specifically, we consider this problem. The objective is the average of local Lipschitz continuous univariate objectives, and the constraint is the intersection of a local constraint sets. We make general assumption on the network model. Our algorithm contains three stages. First, agents construct Chebyshev polynomial approximations for the local objectives. Then, they take the vectors of coefficients of these local proxies as variables and go on average consensus to update these variables. Once the iteration terminates, they obtain a proxy which corresponds to the global objective. Finally, they optimize this proxy by solving semi-definite programs and obtain desired solutions. We prove that the solutions obtained are indeed accurate enough, and that epsilon is any arbitrarily small specified tolerance. Also, the computational and communication complexities of CPCA and eCPCA in our recent work compare favorably with some state-of-the-art. To summarize, we propose CPCA using polynomial approximation and consensus. It has these major advantages for the considered problem. If you are interested, you are welcome to visit our group's website for further details. Thank you.
Hi, my name is Isaac Weintraub. Today, I'm going to be talking about my paper. Hi, my name is Isaac Weintraub. Today, I'm going to be talking about my paper entitled Maximum Observation of a Faster, Non-Maneuvering Target by a Slower Observer. If you look at the picture on the right, we see the target aircraft in red and the observer with his observation radius in blue. The problem statement that we're after is what strategy should the observer take to maximize his observation or encompassing of the target inside his observation radius for as long as possible when he is slower than his target. By considering a constant velocity scenario where the observer and the target's velocity are held constant, the control is the heading of the observer. The optimal control is one which maximizes final time. Final time is defined at the instant the target leaves the observation radius. To solve the optimal control problem, we begin with forming the Hamiltonian, which is the inner product of the co-states and equations of motion. Next, we formulate the necessary conditions of optimality, which come from the calculus of variations. Taking the partials, we obtain the state dynamics, co-state dynamics, and optimal control. Using the transversality conditions, we find that the angle from the observer to the target at final time is the same as the optimal heading. The exposure time is a function of the observation radius, the speed ratio, and the aspect angle between the target and the observer at initial time. By setting the observation time to 0, we're able to find regions where the observer is unable to make any observation of the target, independent of whatever control he decides. Let's consider an example. In this example, the observer takes the optimal heading. The figure on the right shows the instantaneous range between the observer and the target and the observation range of the observer. We see in fact that observation is invariant during the scenario. By assuming the observer takes an optimal strategy and sweep through all possible initial aspect angles between the target and the observer, we observe that some aspect angles preclude the observer from making any contact with the target. These aspect angles are highlighted in green. The figure on the right shows our example scenario overlaid on top of the observation limison in blue and the zero observation region in green. It was a joy posing and solving this optimal control problem. Thank you for taking the time to listen to this talk. Have a nice day.
Hi everyone, my name is Kananat Kuwalanan, and today I'm going to Hi everyone, my name is Kananat Kuwalanan, and today I'm going to present my work on the set of possible minimizers of a sum of known and unknown functions. This is a joint work between me and my professor Shriya Sundaram. First, I will discuss about a learning problem as a motivation. Suppose there are m agents, and each agent holds the dataset di. The objective is to minimize the sum of the loss functions, or big L here, with respect to the common parameter w. However, if one of the dataset has not been reported to the server, we cannot calculate the exact minimizer of the function big L. One of the possible questions is that, given some characteristics of the loss function of agent M in which the data is missing, can we estimate the set of possible minimizers? Formally, we consider the sum of known and unknown functions. The unknown function is assumed to be sigma strongly convex and have the minimizer in the set A. Our goal is to characterize the set that contains the minimizer of the sum denoted by M. The descriptions of M are just our assumptions on the unknown function and first-order optimality condition. In our paper, we consider two scenarios, one of which is that the set A is a general compact set, and the other is that A is a ball. We provide a necessary condition for each case. However, the condition corresponding to the first case is computationally expensive to verify, while it is cheap for the second. In addition, we also provide an algorithm for estimating M when the set A is a ball. In the numerical example shown here, we set the known function to be a quadratic function. This function is shown by the level curves in the figure. For the unknown function, we choose the strongly convex parameter to be 0.25 and the set A to be a ball centered at the origin and radius of 0.8. Finally, using the proposed algorithm, we can estimate the region that contains the possible minimizers, which is shown by the dark blue region. Thank you very much.
Hello, welcome to the talk, a generic solver for unconstrained control problems with integral functional objectives. I'm Shihao Zhen. In this paper, we consider the unconstrained control problem, UCP, where its objective can be written as an integral functional, and the goal is to find a set of controller functions to minimize the value of the functional. The problem is unconstrained in that all conditions can be embedded in the objective. For each controller function, the objective functional can be decoupled into two terms. One integrates a function of the controller over its domain, and the residual term does not depend on the controller. Several control problems can be expressed as unconstrained control problems, such as the well-known Wittenhausen's counterexample. Finding the optimal or even just some good controllers to UCP is not trivial, and it is usually done on a case-by-case basis. To tackle UCPs in a principled way, we provide a generic algorithm to approach UCP numerically. And we want to let it as easy to use as possible, so we developed a solver for the algorithm. To make it compute faster, we also parallelize the computation by GPU. The idea behind the generic algorithm is to start from feasible controllers and keeps improving them by locally searching over some good candidate sets. For more details about the choice of the candidate sets, please refer to the paper. Let's now see how well the resulting solver performs. We try to find the optimal controllers to the Witzenhausen's counterexample. The existing algorithm converges much slower than our solvers, which are in red and blue in this chart. We also apply the solver to other problems, such as the zero delay source channel coding and the two-dimensional Witzenhausen's counterexample. And the solver is able to find those nonlinear controllers efficiently. In sum, we provide a generic algorithm for UCP and develop a generic solver accordingly. The solver numerically finds nonlinear controllers, and it is much faster than existing methods. Thank you. My contact information is listed below in case you have any question.
This talk is about how robust control can be used to synthesize first-order iterative algorithms. My name is Laurent Lessard, and this is joint work with Peter Seiler. Most optimization and machine learning problems are solved using iterative algorithms. For example, if we can evaluate the gradient of f efficiently, we might do something like gradient descent to find the x that minimizes f. Depending on what we know about f and how we choose algorithm parameters, such as the step size alpha, we might be able to guarantee a certain convergence rate, rho, where a smaller rho means faster convergence. In this paper from 2016, we developed a framework for analyzing optimization algorithms by treating them as robust control problems. For example, gradient descent can be written as a feedback interconnection of grad f, which is the uncertain plant, and an LTI system, which is the algorithm itself. The benefit of this approach is that more complicated algorithms, such as Nesterov's fast gradient method, that require storing additional past iterates, can also be represented in this way. The main result from that work had the following form. If you specify the algorithm you want to analyze, in this case by providing state space matrices A, B, and C, and you specify constraints satisfied by the inputs and outputs of the function, which are IQCs pi1 through pi k, then we can solve a small convex program to find the combination of IQCs that certifies the fastest possible convergence rate rho. The key point here is that the algorithm is fixed. If we wanted to optimize over algorithm parameters as well, then the problem would no longer be convex in general. In the present ACC paper, we show that if we swap the two assumptions, the problem remains convex. In other words, if we fix the combination of IQCs, then we can find a convergence rate bound that holds for all algorithms. And this includes algorithms with arbitrary but finite memory. Let's look at a simple example to compare these two results. We'll consider algorithms acting on functions with sector-bounded gradients. In 1D, these functions have a gradient whose graph is contained in the shaded region, with upper and lower slopes L and M. We can represent such functions with the following quadratic constraint. To use the previous result, we must specify an algorithm. If we choose gradient descent with the following step size, then we get this upper bound on the convergence rate. So gradient descent is at least this fast on this class of functions. But this result does not tell us whether there might be some other algorithm that is even faster. If we apply the new result from our ACC paper, we get a result that holds for any algorithm with arbitrary but finite memory. The new result is a lower bound that says that the worst case convergence rate is no faster than this. These two results together prove that gradient descent is in fact optimal for this function class. This was just a simple example, but in our paper we also study more complicated cases where an algorithm with more states is required to achieve optimal performance. If you're interested, I encourage you to take a look. Thank you.
Hello everyone, today I'd like to talk about some new results on stochastic compositional optimization. My name is Tianyi Lin from UC Berkeley. This is a joint work with Chen Yufan, Mengli Wang, and my advisor Michael Jordan. We are interested in solving the problem called convex compositional optimization, where the objective is the sum of smooth convex function and another non-smooth convex function. The smooth convex function is a composition of two functions which has a finite sum structure. Each component function is not necessarily convex or monotone. One typical application is on-policy reinforcement learning, which you can find in Saturn's book. The minimization problems is equivalent to solving the empirical Bellman equation using the loss function. Here, gamma is discount factor and pi pi r pi are pairs of transition matrix and reward vectors sampled from a simulator. The basic idea for solving these problems is using stochastic compositional gradient, which fully explores the structure of the problem. At each iteration, we construct a CT, which is an estimate of the true gradient, and perform one-step proximal gradient update. However, CT is not necessarily unbiased estimate of true gradient because of the red part, and makes the analysis more challenging. We can also use a variance reduction to reduce a variant of CT and improve the complexity bound. At each iteration, we set the initial iterate for the inner loops as the reference point from the last iteration and perform empty step proximal gradient updates with the variance reduced compositional gradient. At each inner loop, the variance reduced compositional gradient is constructed using these three equations. So the standard setting assumes MT as a constant, and the reference point for the next iteration is as the last iterator of the inner loops. In this table, we list all the complexity bound of all methods. Our contribution is to propose a first algorithm that can achieve the near linear dependence on m plus n. The key components for our algorithm are three aspects. First, the number of inner loops increases as the epoch count grows. Second, the reference point for the next iteration is set as the averaging iterate. Third, the step size is diminishing. The proof techniques are mainly based on conditional sub-martingale inequalities. We conduct experiments with all the methods listed in the table. The problem is chosen as a sparse mean variance optimization with relatively large data sets. You can see the results from these three figures that our algorithm consistently outperforms 4 baseline approaches. If you are interested in the results of our paper, please come to the post session in ACC 2020 or see our paper in archive link. Thank you so much.
Hello everyone, my name is Vincent Roulet and I'm going to present to you our last work with Mariam Fazel, Siddhartha Srinivasa and Zaid Arshawi. So we were interested in control programs where, for example, you want to move the arm of a robot such that its hand reaches some target in a finite number of steps where each step is defined by the discretization of physics law. In particular, we will be interested in the case where some noise can perturb the dynamics at each step. For example, you can imagine a random force that is applied to the movement. And the classical objective would be then to minimize the average of all potential realizations of the noise of a cost and the trajectory defined by the controls and perturbed by the noise, plus some regularization. So rather than minimizing the average of this cost, we will be interested in a risk-sensitive formulation that minimizes the logarithm of the expectation of the exponential of the cost. The idea behind this formulation is that it captures not only the average cost, but also higher order moments defined by the noise, such as the variance and so on. And hopefully the solution will then be more robust to the noise. In practice, if I was taking a function that had some sharp minima, by applying this log some X transformation, I will remove the sharp minima and only the most stable minimizers remain. And our hope is that the solution of this risk-sensitive objective will be more robust to any noise that is applied to the system. The algorithms used to solve this problem are the following. If the dynamics are linear and the cost quadratic, then you can solve the problem by using dynamic programming. If they are not, people use as a heuristic that they find the linear quadratic approximation of the movements on the current controls that they have, and they use the linear quadratic solution offered by dynamic programming. So our question was, can you prove anything about this heuristic? Does it converge? And is there any line search that is reasonable and so on? So we took an optimization viewpoint and we identified a surrogate risk-sensitive cost that can be minimized by a regularized version of the previous algorithm, we can then have access to inline search, and we can then prove convergence to a near stationary point. In terms of numerical illustrations, both algorithms behave similarly, but our surrogate cost can be computed like exactly rather than the noise that you would have by using a Monte Carlo approximation. And finally, we have a code that was implementing this strategy on simple synthetic problems, and we observe what we hoped for, that is to say that for a random noise of increasing strength, our robust or risk-sensitive solution is more robust. Thank you.
Hi, everyone. My name is Drew Scott. I'm a master's student at the University of Cincinnati. Hi, everyone. My name is Drew Scott. I'm a master's student at the University of Cincinnati, and I'm presenting some work we've done on a market-based approach to a length-constrained multiple depot traveling salesman problem. And we're taking this problem, the main problem we're solving is a persistent ISR problem, which involves a set of targets that need to be continuously monitored by some set of vehicles, and the information periodically brought back to some set of control stations. And these targets will have a differing level of urgency, and with that, a maximum amount of time between successive visits. So more important nodes we're visiting more often, less important ones don't need to be visited quite as often. And we compose this as a length-constrained multiple depot TSP, where those length constraints are corresponding to the revisit periods of the nodes. And the objective function we choose to optimize over is minimizing maximum tour length. And this is a more difficult objective to solve than just a normal minimized total travel one. But even though it's more difficult, the market solution provides a simple but effective solution process to optimize over this objective. And we compare this to a mixed integer linear program. And you can see the constraints on the left. And as far as integer programs go, this is fairly efficient, but it's still going to scale exponentially. And for larger problem sizes, this is effectively infeasible in terms of computational time. And to compare this to, we have our market solution, which is treating salesmen as resources, and target nodes are assigning themselves to salesmen of lowest cost. And the prices assigned to each salesman we're updating according to demand. So salesmen with greater tour lengths and number of nodes in them are going to have a price increase, whereas salesmen of lower number of nodes are going to have a decrease in price. And we see that happening here in these figures. So this one's for tour length over iterations, and the tour length in black for tour 5 is the greatest. And we see over these iterations it's decreasing. And that's because in this chart, we see the prices for the same problem. The price for tour 5 in black is increasing over iterations. And as that price increases, less and less nodes are picking that, as it's no longer the one of minimum cost for them. So as less nodes are assigned to that salesman, we see the tour length decreasing then. And opposite is true of the lower tour lengths, their prices decrease. And then with a lower cost, more and more nodes will want to be assigned to them, and then making their tour length greater. And we can see as this, in the later iterations, we're approaching all the tour lengths being similar, which will happen when you're minimizing maximum tour length. That's what's going to end up happening, is all the tour lengths squeezed together to be very close. And we have results here. We see the MILP and the market scaling differently. The MILP is scaling very poorly, and the market is scaling well. So for 50 targets, it takes the MILP about 45 minutes, the market less than a second. And we scaled the market up to about 500 nodes. It's still able to solve that in just a few minutes, which is a very large problem size that's effectively infeasible for the MILP.
Hello, I am Jamin George, and I'll be presenting our 3-minute pitch on our paper. Hello, I am Jamin George, and I'll be presenting our 3-minute pitch on our paper. Our paper is titled Multi-Agent Coordination for Distributed Transmit Beamforming. Here is an outline of the talk. I will present the problem description, then propose 2 solutions and numerically comparable solutions, and conclude the talk. Now, the problem consists of n mobile agents located in some 2D space, and each agent is transmitting at a low VHF with amplitude A and phase alpha. And the radiation pattern constructed by the n agents are given here. And the goal objective is to adjust the agent positions and their amplitude and phase such that the constructed radiation pattern match a desired radiation pattern. We also would like to minimize the total distance traveled by the agents, or the total relocation of the agents, which is given by this integral cost. So the first approach to this problem is an open loop approach, where we assume we know the objective function, we know the expression for the objective function, and we simply take a gradient flow. We take a fast gradient flow for the amplitude and the phase, and a slow gradient flow for the motion. The closed loop approach assumes we don't know anything about the objective function or the radiation pattern, but we assume we do know the motion penalty term because it's given by the user, is described by the user. So that we use an extremum seeking control to adjust our amplitude and phase that depends on the unknown objective function, while we use the gradient flow to minimize the motion penalty term. Here we present the here we compare the numerical simulation for both approaches. Here we have a desired pattern. It is constructed by 5 agents located at the star locations. The initial position of the agents is given by the circles, and the final position is given by the asterisk. So the initial pattern for initial position are the same for both approaches, and the initial pattern is given here. And the final pattern is constructed by the agents after running the algorithm for a while. And you can see that the final positions obtained by each of the agents are different, but they were both able to reconstruct the desired pattern to some degree. So now we conclude our presentation. So we propose 2 approaches. One is an open loop approach, the other one is a closed loop approach. And our future work is given here, and which is also presented in our paper. Thank you.
Welcome everyone. My name is Seth Ta, and today I will be discussing a method for increasing the efficiency of grid-free path planning by bounding the search region. So whenever we plan paths through an obstacle field, we need to specify the region that the potential paths can go through. We often do this either explicitly by specifying certain boundaries or implicitly by placing all our obstacles within a certain region. The remainder of this presentation will focus on a 5-step method to bound the search region concurrent with the path planning process. And the overall effect should be to increase the time efficiency of the path planning process. So the first step is just to determine whether the goal point is directly visible from the current location. If it is, then fantastic. The shortest path from this point to the goal is a straight line. However, if it's blocked, then we need to move on to step 2. In step 2, we need to find a feasible path length. This could be any path between the start and the goal that goes around the obstacles. And so whatever the fastest way for you to find this path is, that should be the method that you use. From there, we can then create a boundary around all the points that can be reached in a trajectory through the start and goal points with a length equal or less than the length of that feasible path we just found. So when you do that, what you find is that there's a boundary that is an ellipse around your starting and goal points that encompasses all the points that can be reached with a distance equal or less than that feasible path length. But for simplicity and for quick calculations, what we have done is bound that ellipse by a rectangular box in order to speed things up. So step 4 is to determine all the points that are bound and visible from the current point. So this is essentially doing the first part of a visibility graph where you find all the different points that are visible within this region. However, instead of calculating the entire visibility graph within the search region, you then simply find which point you want to go to next. This can be done using a heuristic or whatever method you decide to use. You then need to go to that point and essentially repeat this process. So go back to step 1. You can then find the next boundary, the next point, and continue this process until you reach the goal. When you do this, you'll find that you have the path that you were looking for. In the graph on the right, we compared our method to a grid and a visibility graph version of A star, and we found that our hybrid version here performed better. I want to thank our sponsor for funding this project, and I want to thank you all for your time.
Hello, my name is Cemal Tuğrul Yılmaz.
Hello everyone, this is Purya Karimi. I'm going to present our work about design a high efficiency and low ripple BLDC motor based on multi-objective optimization method. The authors of this paper are me, Vahidi Zedi, and Dr. Amir Qasemi. The goal of this paper is to maximize the efficiency and minimize the torque ripple of a BLDC motor. Both efficiency and torque ripple are a function of a rotor slot geometry. As you can see in the picture, we have 6 design parameters, which it reduces to 4 independent design parameters by using the equality constraints in the standard formulation. To this end, 2 steps are presented in this paper. First, meta-modeling to determine an estimated model of F1 and F2 from the simulated dataset using ANSYS Maxwell software. Second, using genetic algorithms to determine optimal Pareto frontiers such that F1 and F2 are optimized. The first step is to determine the design points using full factor rule design, in which number of sample points are equal to n to the power of m, where n shows the number of design levels and m is the number of variables. So we have 4 variables as stated in the previous slide, and we compare 2 and 3 levels of designs, which gives us 16 and 81 different values for efficiency and torque ripple. Second step is to create an explicit function which fits the design points by meta-modeling. We used linear polynomial regression, linear, cubic, CS30 and CS31 function as radial basis function, or RBF. And finally, by reaching to the explicit function using meta-modeling, we do the adaptive multi-objective optimization to increase the efficiency of the motor while reducing the torque ripple in the same time. The method we use is a non-dominated sorting genetic algorithm, NSGA2, which is a search-based method and starts with an initial set of solutions. Next, it updates the set with the use of non-dominated solutions in order to reach the Pareto frontiers. And here you can see the results for both linear regression method and RBF CS31. As you can see, the linear regression method does not demonstrate a convex set behavior for lower number of sample points. On the other hand, the RBF CS31 generates a convex set for both low and high number of sample points, so we can use this method to predict the system behavior. Thank you so much. Please let me know if you have any questions.
Hello, my name is Cemal Tuğrul Yılmaz. I am a PhD student at North Carolina State University, and this research has been done with the collaboration of US Army Research Laboratory. Our research title is Observer-Based Extremum Seeking Control of Static Maps with Delays. Here we consider minimization of unknown nonlinear map Q of U, and we have 2 assumptions regarding the map. It is continuously differentiable and strongly convex. We measure this unknown function with a known and constant delay. Our aim is to design an extremum seeking control to optimize this function. We compared some extremum seeking algorithms in this table. These 6 papers design delay-free and delay-aware controllers by applying a periodic perturbation. This perturbation is replaced with a stochastic perturbation in these 2 studies. This paper developed an alternative perturbation which doesn't necessarily need to be periodic or stochastic. We extend their result to compensate input-output delays, which is much more realistic scenario. The only requirement for the selection of our perturbation signal is the persistent excitation of the controller. Moreover, the other advantage of our design is that it doesn't require any averaging analysis to prove convergence. A schematic of the closed-loop system is given in this figure. We measure this unknown function with a delay, and the output signal is used in this adaptive observer, which gives us the estimation of the gradient, theta hat. Multiplication of this theta hat by controller gain k plus d constitutes our controller u dot, and we obtain u. This jitter signal should guarantee the persistent excitation of the controller. Our theorem 1 says that our closed loop system exponentially converges to a small neighborhood of the optimum point. Here we consider a static quadratic map as an example. We measure this function with 4 seconds delay. We choose our data signal as a normally distributed random signal, as given here, and we design our external signal controller as this expression. And this figure shows that the extremum seeking controller without delay compensation is not able to converge to optimum point, whereas our proposed controller converges to optimum point. This figure shows the evolution of proposed control inputs and their optimal values. And the final figure shows the norm of the gradient estimation error with respect to time. Thank you.
All right. Thank you, everyone.
That was a wonderful session.
A lot of material. So thank you for coming to this is the rapid portion of the rapid interactive session on optimization and optimal control. So please do vote for your favorite talk in the People's Choice link, which is in the chat. And we're going to close the voting at noon today. So please do vote for your favorite. Okay, so now this is the end of the rapid portion. The second half of the session is the interactive portion. Okay, so at this point, you'll leave this Zoom room and go back to the main conference program, and you can see the at 11 o'clock in the main conference program today, you can see the sessions for each of the 22 presenters has their own Zoom link, and so please go visit them. Now, it's sort of like a poster session. Go visit the ones where you are particularly interested and have questions. So we don't have time for questions, in this rapid part, but the interactive part is the time for questions. So you'll go and you'll visit each room individually, or the ones that are most relevant where you have questions. So please do go visit them in the second part of this session. But please do be sure to visit. So it says, can you please repost the voting link? Sure. So it looks right here, but I'm happy to repost it. Okay, and I also posted the Hugo Schuck link. So if you'd like to nominate one of these papers also for the Hugo Schuck Best Paper Award, the link is provided there. Great, so please do go back to the main conference program Wednesday, scroll down past this 9:30 set of links, and go to the 11 o'clock links for the rapid interactive session. And we're going to have sessions like this tomorrow morning and Friday morning. So just 2 parallel sessions. And so I hope you enjoyed it, and look forward to seeing you around the conference. Thanks, everybody.
Okay, bye. Great.